In this video, we're going to take some measurements regarding buoyancy of some different cubes that I have here. I should note all of these are actually 1-inch cubes of different material. And I have brass, steel, aluminum, some sort of clear plastic, and some type of wood. And what I want to do with these is, again, get some quantitative measurements that will help us understand the concept of buoyancy a little bit better. So on my screen, I still have my gas pressure sensor measuring atmospheric pressure. It's actually a little bit less than it was in my previous video. We actually do have some stormy weather on the way, so the pressure is decreasing, probably due to the weather system that's coming. And then I have a force sensor measured here. I'm going to need to re-zero that in a moment, and I'll explain what I'll be measuring with that as well. So let me go ahead and get that re-zeroed. So we have that zeroed. We also are going to need a data table for this. So I've got my materials listed here in the first column. I'm going to record the mass using this electronic balance just so that we have it. You can also make some conclusions from that. I'm going to measure the weight of the objects directly using the force sensor. When we submerge the cubes in water, we're going to measure the force, the tension force that's left in the string. I'm just going to record that as force, so this is the force sensor reading. And then buoyant force is not something that we will be able to directly measure, but we should be able to infer the value for each of our materials. So let's go ahead and get started. I'm going to re-zero the scale. I'm going to take my brass cube and put it on the scale. And the reading is 137.25 grams. So 137.25 grams is the mass of the cube. Now I could convert that to kilograms and multiply by G, 9.8 newtons per kilogram, to get the weight. And you might do that on your own. But I'm going to go ahead and measure the weight directly by simply hanging, and I have a little piece of thread around the cube so that I can hang the cube from the force sensor directly. And so I need to get it still, and we can look at our reading here, and it looks like we have a reading of, let's call it 1.3, and it's fluctuating a little bit. Looks like it's hanging out at 1.32. Yeah, let's go ahead and call it 1.32, realizing that there's going to be a little bit of measurement error there. Okay. Now, if I were to draw a force diagram for the cube at this point, what I'm directly measuring is actually the tension force upward in the string. Of course, gravity is pulling down on it with the exact same amount of force if it's not accelerating up or down. So although I didn't directly measure the weight, I've measured the tension force. We can assume that those two are the same at this instant. So I want to look at what happens when I lower the cube into the water. So you can kind of see what happens to the force reading as I shift this around. Get it right where I want it. And as I lower it into the water, we should see the readout become less. So now it's completely submerged. And my force reading has lowered to about 1.1, again it's fluctuating, let's call it 1.17 newtons. So the weight didn't change, but the tension force certainly did. The tension force reading is now 1.17 newtons. And before, we knew from the previous measurement that the weight was 1.32 newtons. Now the cube is not accelerating, it's completely submerged in the water. So whatever forces we have need to be balanced. Now the tension force did decrease, we know that. But what I can say now is there's a buoyant force also pushing up on the cube, okay? So that buoyant force, I'm not gonna be able to measure it directly, but I can infer what it is based on the weight and the tension force. The buoyant force needs to make up the rest of the force to get to 1.32 newtons, right? So if I just take the difference between these, 1.32 minus 1.17, I can make the inference that the buoyant force is 0.15 newtons, okay? So I didn't directly measure it, but I can infer the buoyant force by comparing the out of water weight of the cube and then the submerged weight of the cube. So in this case, I would go ahead and fill in my values for brass. The weight was 1.32 newtons. The force measured when submerged was 1.17 newtons. And we're inferring that the buoyant force is 0.15 newtons, okay? We're gonna do a similar thing for each trial. Now, one thing I wanna show you is that if I lower the cube so that it's still submerged but not touching the bottom, I should still see a reading of 1.17. It fluctuates a little bit, and that's, again, we have some measurement error there. But when you submerge something, as long as you don't get really, really deep, so that the density of the fluid changes, it doesn't matter how deep you are in the fluid, the buoyant force will be the same as long as you're measuring the same object, okay? So it's fluctuating a little bit, but it's still staying put mostly at 1.17, okay? So now I can make the measurements a little bit more quickly. I'm gonna go ahead and remove the brass piece. Now it's wet, so I'll put it on a towel. And next up, I will do my steel cube. So same size, it's a 1-inch cube. According to this, my mass is 126.99 grams. So 126.99. Next, I'll get the weight, direct measurement of the weight using the force sensor. It's not in the water at this point. And I'm getting a value of, again, it's going to fluctuate a little bit, 1.2. Again, so it's not spinning. That can actually influence the readout. Let's call it 1.2. 1.2. As soon as I say it, it fluctuates. Let's call it 1.23, knowing that we might have a plus or minus 1/100th of a Newton issue here because it is fluctuating. So now I want to submerge it. It's completely submerged. And I'm getting a readout of about 1.07 newtons. So that again would go in this column. It's really the tension force reading when it's submerged. And again, I get some fluctuation there. So just keep in mind there's a little bit of measurement error in that last decimal place. You could go ahead and calculate the buoyant force there as the difference between those two readouts. Next up, I'll do the aluminum. The aluminum mass is 44.04 grams, 44.04. We'll get the weight next. Looking like about 0.41 newtons. is the weight. Okay, that one looks pretty stable actually. Let's go ahead and lower it into the water. Now it is completely submerged. And it's looking like 0.25 newtons for the force sensor reading when submerged. Maybe again fluctuating a little bit. I think it's staying at 0.25, a little bit more. So again, we know there's going to be a little bit of measurement error there. And next up, the clear plastic. The mass I have is 18.33 grams, 18.33. Let's go ahead and get the direct measurement of its weight. That's straight. The weight is 0.16 newtons, 0.16. Let's go ahead and submerge it. It's fluctuating between 0.01 and 0.02. It's going to be a judgment call on this one. Let's go ahead and go with 0.01. It's tough, right? There's going to be some error there. I'm going to go ahead and write down 0.01, realizing that there's going to be a little bit of give or take in that last decimal point of the measurement. All right. Notice on that last one is that the tension force almost went to 0, right? So let's do this piece of wood next. Its mass is 6.93 grams. 6.93 grams. The direct measurement of the weight looks like it's fluctuating. It's a very small force, doesn't have much mass. Let's call it 0.06. Now this one's going to be a little bit different. I'm going to try to submerge it and let's see what happens. Floats, right? There is no tension force there. So I still want to have some sort of measurement of the buoyant force. So I'm going to have to change my approach a little bit. I'm not actually going to be able to use the hook side of the force sensor. I'm going to take that off. And what I'd like to do is actually force the cube underwater, just underwater, and measure that force. Okay, let me get that set up. I've got the bumper side of the force sensor. Because it has a different piece on the bottom now, I do need to re-zero it. And this is the tricky part. I'm going to try to submerge the cube and just push it with the bumper so that it just gets below the surface. This will be tricky. So I'm trying to get the bumper just at the surface of the water and get that to kind of balance. See a little air bubble. So this one might be the toughest of the measurements to get, but I'm seeing a value of negative 0.0, let's say 9. So negative 0.09 newtons. Now let's think about what that means. What I've done here is change the force diagram, right? So now it had its own weight, which was pretty small. The weight was 0.06 newtons. And the force sensor is now also pushing down on the cube. So I'm going to have a downward force of 0.09 newtons from the force sensor. Okay. So now, because it's not accelerating up or down, the buoyant force, which is upward, is actually going to be the sum of those two numbers, right? So the buoyant force is coming out to be 0.09 plus 0.06, or about 0.15 newtons, okay? So I have to take a different approach on that, but I can still get to that buoyant force. Your job now, if you haven't already, is to calculate the buoyant force in each of the trials and see what patterns you see. You should see a definite pattern. Knowing again that our force measurements might have a little give or take at the hundredths place, the second decimal place. And I want you to think about what would be similar in each case that would result in the buoyant forces that you're seeing. And that's something that you can think about and you should discuss later with your teacher. Thanks for watching.